Hey guys, welcome back. In this video I just want to introduce nodal analysis and how we can use it to solve circuits that are not just simple series or simple parallel circuits. So this is also really useful for problems that have two power sources like this one. And yeah, it's one of the available methods. There are other methods too, but this one is called nodal analysis. Some people call this node branch analysis, I think, but I was introduced to this method as nodal analysis by my highly respected PhD professor of electrical engineering, so I'm going to stick with the name that he used. But basically this method is just applying KCL, or Kirchhoffs current law, at nodes. So when we look at this problem, we have 1, 2, 3, 4 nodes. And what we want to do in nodal analysis is we want to pick one node to ground it. It's not really a real ground, but it's just the reference that we're going to take as 0 volts for all of the other voltages. And in cases with voltage sources, especially more than one voltage source, if you can ground the node that's connected to one or more than one voltage source, that's going to be a good one for us to take reference. So let's draw on a ground here. So this node is going to become our 0 voltage for the rest of the problem. When you look at the other batteries here, then you can see it's going to step up 3 volts and step up 2 volts. So we already know the node voltages up here is going to be 3 volts. And this node is going to be 2 volts, which only leaves one unknown voltage, and we can give it any name that we want. Let's just call it VA for this problem. But we basically need to find this voltage before we can apply Ohm's law to these resistors, because we don't actually know how much current is coming out at the moment. So for nodal analysis, basically the number of nodes with unknown voltages are going to equal the number of equations that we have, and then we'll be able to just use back substitution or a matrix or whatever to basically find all of our unknowns, because it will be determinate. And the way that we do it is we basically just do KCL at the node. So what we're going to do is we just assume a current coming into and out of the node at all possible branches. So you can just label on the currents that you think there are. It doesn't matter which way they go, but if you think you know it, you can try putting them on as you think. So we can call that one I1, we can call this I2, and let's say that we think I3 is going to be going this way. And by assuming a direction of the current through a resistor, that means we're also assuming the polarity of the resistors, because current is always flowing from higher voltage to lower voltage across resistors. So that means that we've assumed the polarity like this for all of the resistors. But if you remember from passive sign convention, the assumption of the polarity doesn't matter. Just if we find that the current to be negative in the resistor, then it just means the polarity was the other way around. So we'll find out if we have these backwards later on in the problem. But yeah, that's basically what's going on here. So we're assuming that VA is lower voltage than 3 volts and 2 volts, and it's also a higher voltage than 0. So now we just write KCL for each unknown node. So in this case there's only one, so we're going to write KCL for A. And just pick a convention and go for it as for what's positive and negative. I like to use positive is flowing out and negative is flowing in for the currents. So when we write the expression KCL, basically the sum of currents has to equal to 0. So I1 and I2 are flowing in, so they're going to be negative, and I3 is positive, so it's flowing out. So let's maybe write that one first, so we have, just so it looks a bit nicer, we have I3 minus I1 minus I2 is equal to 0. This is the expression for Kirchhoffs current law for the whole node that we're calling A. Now if you remember Ohm's law, we have V equals IR, and we can rearrange this to be I is equal to voltage over resistance. So we just need to get these in terms of the voltage and resistance, and we actually can write those. So let's start with I3. The voltage across this resistor is VA minus 0, because we've assumed that VA is higher, so when we subtract the lower one, this is going to be the voltage drop. And then we divide this by the resistance, which is 1 ohm. Then for this resistor that I1 is flowing through, the voltage, first of all we subtract this one, and the voltage is 3 volts minus VA. Again, we've assumed that the current is going this way, so that this is the higher voltage. So the difference between them is the bigger one minus the smaller one. So that's why we have 3 volts minus VA. And then we just divide that by the resistance, which is 2 ohms. And then for the other resistor we do the same thing. So the voltage drop across the resistor is 2 volts minus VA. Again, we're assuming 2 volts to be bigger, so we're subtracting the VA, which is the smaller one, over the resistance, which is 4 ohms. And I've ran out of space, but that's all equal to 0. Okay, so we just want to simplify this. You can see there's only one unknown in here, so one unknown and one equation. That's pretty easy. Let's multiply everything by 4 to get rid of these numbers on the denominator. So we have 4, 4, and 4, and then we can just divide this basically. That's going to be nothing. This 4 and this 2 are going to cancel, so we have minus 2, and then this 4 divided by the 1, that's basically just ignore the 1. So let's maybe write this a little bit cleaner. We have 4 times VA minus 2 times 3 times VA. I'm going to drop the units of ohms and volts because it gets confusing when you have the V here for volts and VA for the unknown variable. So basically each term is going to be in units of volts over ohms, which is in units of amps. The whole term is. So we can close that bracket, and then we just have minus 2 minus VA is equal to 0. So we can simplify this a little bit, and we get 4 VA minus 6 plus 2 VA minus 2 plus VA is equal to 0. So basically we get 7 VA is equal to 8, and then we can just rearrange for VA and find that this is about 1.143 volts. So yeah, we found the voltage now of this node, but it's probably also useful or requested of you to find the currents that are flowing through where the voltage drops across these resistors. So let's quickly do that. So we have V1, V2, and V3 for the voltage drops across the resistors corresponding to each of the same currents, 1, 2, and 3. So the voltage drop across the first resistor is 3 volts minus 1.143 volts, and that is just equal to 1.857 volts. For V2, we have 2 minus 1.143, and that's equal to 0.857 volts. And then for V3, we just have 1.143 minus 0, so that's equal to 1.143 volts. And then when we want to solve for the currents for each of those, we have I1, I2, and I3. Well, the current again is just equal to V over R, so we have 1.857 volts over 2 ohms, and that gives us a value of 0.929 amps. And then I2 is just 0.857 volts over 4 ohms, and that gives us 0.214. And then for I3, we have 1.143 volts divided by 1 ohm, and that gives us 1.143 amps. And just to double check, when we look at this, we have for KCL, Kirchhoffs current law, at the node, we have I3 minus I1 minus I2. So basically the sum of currents flowing in equals the sum of currents flowing out, and that checks out because I3 minus I2 minus I1 equals 0. So it looks like we've done this problem correctly. So yeah, that's nodal analysis, and join me in the next video and we'll do a slightly more complicated problem also using the same method.